Welcome to Abhi's Math e-Pathshala. Today's topic is maximal ideals in rings.
Okay. So, so today our topic of discussion is maximal ideal and prime ideals in rings. And let me introduce uh, first what does it mean by a maximal ideal in a ring. So, uh, actually, these type of ideals will give you some beautiful uh, characterizations of quotient rings of a ring. So let me first define maximal ideals. Maximal ideals. What is the definition? So you need to take a proper ideal M of a ring R, which is said to be, which is defined to be a maximal ideal of ring R whenever I be an ideal of R satisfying M subset of I subset of R, then one of the two possibilities will hold. That is, either I is going to be M or I is going to be the whole ring R. So there are two possibilities. That is, a proper ideal M is defined to be a maximal ideal of a ring R whenever if you can construct an ideal I satisfying M subset of I subset of R, then either I will be M or I will coincide with the whole ring R. So there are two possibilities. So that means in between M and the ring R, there is no other proper ideals. Let us try to find. So firstly, let us try to find out the maximal ideals in the ring of integers. Ring of integers. So this is our basic model of ring of integers. So that is why we are trying to find out the maximal ideals in Z. What are those? Now it has been proved that the list of ideals of Z must be nz, where n is 0, n may be 1, n may be 2, and so on. So it has been proved that the list of ideals of Z must be nz. where n equals to 0, 1, 2, 3, and so on. So this is the list of ideals, that is any nz. So we need to find out the maximal ideals amongst these ideals nz. So what are the possibilities of an ideal to be a maximal ideal in Z? So let us have a look, an observation that let n be a prime. Let us consider that small n be a prime number. And we show that for, for this prime n, the ideal nz is maximal. So this is our first guess. What the maximal ideals should be. That is, if we consider a prime n, then nz will be maximal. So to prove this, so let us consider an ideal mz satisfying that mz will lie in between nz and the ring of integers. Satisfying nz is lying in the subset of mz, subset of z. Now note that Z is a ring with unity. So 1 belongs to Z, and so for this reason n is n1, and that is why it belongs to nz. But nz is a subset of mz. So this n is a member of this ideal, which implies that m divides n. Since n is a member of mz, so this means m divides n, that is n can be written as some multiple of m for some integer q. But we have assumed that n is a prime, but n is a prime, which concludes that so since n is a prime and m divides n, so either this m must be 1 or this m equals to the n. For which this gives us that the ideal mz is either, for the case m is 1, is coincides with the ring of integers z, or if for the other case whenever m is n, so mz must be the ideal mz. And this proves that by the definition of maximal ideals, this proves that the ideal nz is maximal. So this indicates that what are the maximal ideals in Z may be. So our first choice is for those integers which are prime. So now our goal is to show that nz is maximal. This assumption will imply that the n must be prime. So our goal is, if nz is maximal, then n must be a prime. There is no other choice of n's. So the only possibilities are for those n which are primes, and this will give you the complete list of maximal ideals. So this is our goal. But suppose, if possible, n is not a prime. So that means n is a composite, that is product of two integers which are lying in between 1 and n. That is 1 less than p, q less than n. Yeah. But this shows that since n is pq, so nz will be a subset of pz, and pz is a subset of z. But our assumption is that nz is maximal. So this concludes that either pz equals with nz or pz equals with z. That means either n divides p or p divides 1. But in both the cases are impossible, since n is a prime. Sorry, since p lies in between 1 and n. Yeah. So this leads to a contradiction. Because p will not divide 1, this is impossible, and also p strictly less than n. So for that reason n will not divide p, because p is less than n. And this contradiction implies that, so hence n must be a prime. So thus we have proved that the complete list of maximal ideals are those nz if and only if n is prime. So the complete list of maximal ideals are those nz if and only if n is prime. So this characterizes all the maximal ideals in the ring of integers. Now in the next we are set to characterize the maximal ideals of a commutative ring with unity in terms of the algebraic structure of their quotient rings. That is, with the view of the structure of quotient ring R by an ideal I, which will characterize the maximal ideals in the ring R, where R is a commutative ring with unity 1. So this holds in a commutative ring with unity 1. So what is the result? The statement is, so let us consider R be a commutative ring with unity 1, then a proper ideal I of the ring R is maximal if and only if the quotient ring R by I will form a ring, will form a field. That is, so keeping in mind the structure of quotient ring R by I, we can characterize the maximal ideals in the commutative ring R with unity. So this is another way of viewing maximal ideals in a commutative ring with unity 1 in terms of the algebraic structure of the quotient ring. So the proof will be like that. Now note that since R is commutative, then so is the quotient R by I. For what is the reason? For A plus I, B plus I belongs to R by I, A plus I dot B plus I is going to be AB plus I, but AB is BA since R is commutative. So this is B plus I, A plus I. So this is clear that if R is commutative, so is its quotient ring R by I. Since R has unity 1, then for any coset A plus I belongs to R by I, A plus I dot 1 plus I equal to A1 plus I, which is 1A plus I, that is 1 plus I dot A plus I. So this means 1 plus I, the unity in R by I. So thus R, since R be a commutative ring with unity 1, then so is its quotient ring R by I, having unity 1 plus I. Yeah. Now we need to check that if I be maximal, then R by I forms a field. So let us consider a maximal ideal. So let I be a maximal ideal. let I be maximal in R. So we show that R by I is a field. So what needs to be checked? So since R by I is now a commutative ring with unity 1 plus I, so it remains to check that for every non-zero element in R by I, it has a multiplicative inverse. And for this reason, let us consider a non-zero element in R by I. What does it mean? A non-zero element in R by I means actually a plus I is not equal to the ideal I, because I is the zero of R by I. 0 means I in R by I means. So that is a plus I is not equal to I. That means A is not in I. Now consider a set I plus RA, and this set consists of those elements which look like M plus RA, where M belongs to I, R belongs to capital R. So we have considered this set I plus RA, and observe that capital I is a proper subset of I plus RA. As why it is a proper subset? Because small a can be written as 0 plus 1a, so which belongs to I plus RA, but small a does not divide I, does not belongs to I. And for this reason, I is a proper subset of I plus RA. Yeah. And also, why it is a subset? Since every element of I, small m, can be written as small m plus 0a. So that means small m is also in I plus RA. So that is why I is a proper subset of I plus RA. This is true for all m belongs to I. Proper subset. Now since now note that I plus RA is an ideal in R by I satisfying so satisfying I is a proper subset of I plus RA, and every subset is a every set is a subset of, so I plus RA is a subset of capital R. Now since I is maximal, and I is a proper subset of I plus RA, so together they imply that I plus RA is equals to equal to R. And this implies as 1 is a member of R and R equals to R I plus RA, so this implies 1 can be written as M plus small RA. For small m belongs to capital I and R belongs to capital R. This. And this implies so this implies 1 plus I equals to 1 means M plus RA plus I. That means M plus I. So 1 sorry. So this implies M plus I plus RA plus I equals to 1 plus I. But M plus I equals to I since M belongs to I. So that means RA plus I equals to 1 plus I. So that is R plus I into A plus I equals to 1 plus I. And this means that this A plus I has a multiplicative inverse in R by I. So this proves that A plus I is a unit in R by I. So therefore every non-zero element in R by I is a unit. That means R by I forms a field. So this portion is clear. That is, if I is maximal, then the quotient ring must be a field. Now what about the converse? That is, conversely let R by I forms a field. So it forms a field. So this is our assumption. So we need to show that. So our claim is IB maximal. So this is our claim that IB maximal. And for this, let J be any ideal in R such that I is a proper subset of J is a subset of R. I is a proper subset of J and J is a subset of R. Now since I is a proper subset of J, so there exists a small a belongs to capital J such that A does not belong to I. Since capital I is a proper subset of J. And so A plus M equals to, so it is a non-zero element, A plus I, sorry. So a plus I is a non-zero element in R by I. That is, actually a plus I is not equal to I. So this is not a zero element. So since R by I forms a field, now since R by I forms a field, so A plus I has a multiplicative inverse. Multiplicative inverse. Say R plus I, that is A plus I, R plus I equals to 1 plus I, and it is equal to A plus R plus I, A plus I, and this implies AR plus I equal to 1 plus I equal to RA plus I. That means, so yeah, this, and this implies, so 1 minus AR belongs to capital I. But now since small a belongs to capital I, and I being an ideal, and I being an ideal, then this AR belongs to capital I, and therefore AR equals to uh, then and therefore 1 minus AR plus AR, so it is in capital I, since I being an ideal. So by cancelling these two terms, we have 1 belongs to I, and this is going to be R. So I equals to R. Since 1 is the unity of the ring and an ideal contains an unity, so this is the conclusion. So I equals to I, and this proves that I be maximal. So this proves that I be maximal. So this theorem characterizes the maximal ideals in a ring R, commutative ring with unity R, in view of the algebraic structures of the quotient rings. Now, so let us have a look to important problems. The first one is in the ring of polynomial over the integers zx, the ideal generated by two and x is not a principal ideal. So in ZX, this ideal that is generated by the number 2 and x, polynomial x, it will not be a principal ideal. That is, it cannot be generated by a single polynomial, non-zero polynomial in ZX. So this is the first problem. So let us prove it. If possible, let us assume the contrary. That is, let the ideal this is principal. Principal. That is, there exists a polynomial. That is, there exists a polynomial gx belongs to zx such that the ideal 2x is generated by gx. Now note that these two can be written as 1 plus 0 x. So it belongs to the ideal generated by 2x. But the ideal 2x can be generated by gx. So 2 belongs to the ideal generated by gx means 2 is gx multiplied by some other polynomial hx for some polynomial hx belongs to zx. And this implies now the product of these two polynomials is 2. So what does it mean? What does it imply? So the degree of this polynomial is, degree of 2 is, since it is a constant polynomial, so its degree is 0. So therefore, degree of gx is 0 and degree of hx is also 0. So this implies degree of gx equals to degree of hx equals to 0. Now since their degrees are 0, so gx, hx both are constants. That is, both are integers only. Both are integers. But since 2 is a prime, so that is a special property which 2 has. So 2 is prime and 2 equals to gx hx. But this is an integer, this is an integer. So 2 is a product of two integers. Then the only possibilities are, so either gx is plus minus 1 and hx is plus minus 2, or gx is plus minus 2, hx is plus minus 1. So either gx is plus minus 1 or gx is plus minus 2. Now for gx equal to plus minus 1, now since in zx the only units are plus minus 1. So this implies gx is a unit in zx. And being a unit, and therefore So being a unit, the ideal generated by Gx must be equal to the whole ring Zx, since Gx is a unit. But still, since ideal Gx is equal to the ideal generated by 2nx, but the ideal generated by 2nx is a proper ideal. So how could it be equal to Zx? So this is a contradiction. So but the ideal generated by 2nx is a proper ideal. So it is a proper ideal. So this possibility should be deferred. Now again let Gx is plus minus 2. Then now the polynomial x can be written as x can be written as 2 0 plus 1 x dot 1. So it is in the ideal generated by 2nx, but this ideal equals with the ideal generated by Gx. Now Gx is plus minus 2. So that means this is either the ideal generated by 2 or the ideal generated by minus 2. Whatever it is, they are same, because this ideal consists of those elements which are looking like 2 into px, where px is a polynomial in Zx. So that means x, so this implies x equal to sum to p star x, or p star x belongs to Zx, which is not possible. But why? Which is not possible? What is the reason? What would be the reason? Since the coefficient in x is here 1, but in this polynomial the coefficient will be a multiple of 2. So that means if we equate the coefficients of x, then this will give you 1 equal to sum 2a. But in Z, there is no a which satisfies this equation. So for that reason, this is a contradiction. So in either case, we arrive at a contradiction, and this implies that, so this implies that the ideal generated by 2nx is not a principal ideal. That is, the assumption we have made in the beginning was wrong in Zx. So this is true. This is not a principal ideal. So that means in ZX you have constructed an ideal which is not principal. Now the second problem is check whether the ideal generated by the polynomial x be maximal in ZX. So is it a maximal ideal in ZX? This is the problem. Justify your answer. If it is maximal, then you need to prove, or if it is not, then you should uh, construct an ideal in between the ideal generated by x and the polynomial ring ZX. So justify your answer. So let us prove that. So to solve this problem, just define a map. Phi colon ZX to Z, define Y, phi of fx equals to f0. That is, we are considering the evaluation homomorphism, evaluation at the point 0 belongs to ZX. So phi will be an epimorphism. That is, it is a ring homomorphism from ZX onto Z. Check. So now, since it is an epimorphism, so we need to calculate the kernel of phi, and then it will give that ZX by ker phi is isomorphic to Z. Now what is ker phi? Set of all those polynomials. So that phi of fx must be 0. That is set of all those fx belongs to ZX. So that f0 equal to 0. And that means f0 equal to 0 means the constant term is 0 for these polynomials which are lying in kernel of phi. And since the constant term is 0, so we must have a factor x for each polynomial lying inside ker phi. So that is, it means it is x hx. Suppose if you consider a polynomial a0, a1x, an x to the power n. This is your fx. Then if f0 is 0, then a0 must be 0, and that is why fx will be a1x, an x to the power n, and that means x, a1, a2x, an x to the power n minus 1. So we have obtained a factor x. So this is the way we can represent this polynomial as x hx. That means it is the ideal generated by x, and therefore by first isomorphism theorem, ZX by ideal generated by x is isomorphic to Z. Now by our known theorem, which we have proved in the beginning, that R by I is a field if and only if I is a maximal ideal. So if this is a maximal ideal, then this must be a field. But this ring is isomorphic to Z, which will never be a field. It is at most an integral domain. So since Z is not a field, so Zx by the ideal X is not a field, and therefore the ideal generated by X is not maximal. So thus we have proved that the ideal generated by X in Zx, it is not a maximal ideal. Also, another way, so another way to look into this problem is that if you look at the ideal X, then this ideal X is a proper subset of the ideal we have considered in problem 1, that is the ideal generated by 2nx. And the ideal generated by 2nx is also a proper ideal in Zx. And this implies, so if this is maximal, then at least one of the two possibilities will hold, that is, at least this ideal will coincide with the ideal X, or this ideal will coincide with this ring Zx. But in that case, this is a proper set in this is also a proper set in this. So this ideal will never be equal to the ideal generated by X, nor equal to the ideal and the ring Zx. So this proves that the ideal we have considered generated by X will never be maximal in Zx. So this is another way of looking and solving this problem in this way. Now we have to state the next theorem without uh, giving the proof, which has an important consequence. That is, the theorem states that let R be a commutative ring with unity 1, then every proper ideal of R is contained in a maximal ideal. This is a beautiful theorem, but we will skip the proof. That is, let R be a commutative ring with unity 1, then every proper ideal of R is contained in a maximal ideal. In R, that is, every proper ideal, that is, for any ideal I, proper ideal I of R, there exists a maximal ideal capital M of R, such that I is a subset of M. So I will be contained in some maximal ideal in R. And this theorem will give you a corollary, that is a commutative ring with unity 1 not equal to 0. That is, in that case we are not we are considering that 1 is not equal to 0, because if 1 is equal to 0, then this will give you the 0 ring. So this has a maximal ideal, that is a commutative ring with unity 1 must have a maximal ideal. So what will be the proof? The proof is like that. Just consider the 0 ideal, singleton 0. So this will be a proper ideal in R. And by the above theorem, this ideal will be contained in some maximal ideal. That is, there exists a maximal ideal M of R such that 0 is a subset of M, proper subset of R. And this proves that every commutative ring with unity 1 which is not equal to 0 must have a maximal ideal. Now let us again have a look on the ring of integers and consider the ideal Pz. Consider an ideal Pz, that is, we are considering this ring and consider an ideal Pz. But assuming P be a prime. So we have already proved that this ideal is a maximal ideal. But this ideal, if we closely look at this ideal, we will find that if for any two integers a and b, if their product is lying in the ideal Pz, then what we will have, that is AB will be some PR for some R belongs to Z, and this implies P will divide this product. But since P being a prime, it has a special property that if it divides the product of two integers, then it will divide at least one of them. That either P divides A or P divides B. Now, if P divides A, then A belongs to Pz. And if P divides B, then B belongs to Pz. And this indicates that means what we have observed, that for any two integers A and B belongs to Z, AB belongs to PZ implies either A belongs to PZ or A belongs to PZ. And this observation uh, is related to the property of this integer, that is the prime property of P. Since P is prime, so that is why we have obtained this observation. So these ideals have another special characteristics in terms of primes, and which are called prime ideals. So what could be the definition of prime ideal? We have already observed in the ring of integers, that is, for any two integer a and b, if ab belongs to pz, then either a belongs to pz or b belongs to pz. So in general, if we consider a commutative ring, then a proper ideal P of R is said to be a prime ideal of R if for any two integers AB belongs to Z, AB belongs to R, sorry, A belongs to R, if their product belongs to P, then this implies either A belongs to P or B belongs to P. The same way what we have observed for the ideal Pz in the ring of integers Z. So these ideals are called prime ideals. So for example, for any prime P, Pz is a prime ideal, is a prime ideal in Z. So this proves also that in the ring of integers, every maximal ideal is prime. Now the question will occur that are these the exact list of ideals for every prime P? Hello, কিছু বলছো?